Students, researchers, industrialists, everyone. Uh, Today's webinar contains our introduction, types of aero engine maintenance, levels of aero engine maintenance establishment, maintainability, availability and reliability, gas turbine faults, systems monitoring, current developments, which includes condition monitoring, digitalization of aero engine maintenance, linear aviation maintenance, and we'll get into role of logistics and supply chain management. We'll have some challenges. We'll be discussing all those challenges and the potential solutions to uh, address those challenges. After that, we'll be moving to opportunities. We'll be discussing about the kind of opportunities that exist both in public and private sector for the budding aerospace researchers locally and globally. And towards the end, we will have a conclusion regarding this topic. First, the introduction part. The demand for airlines has increased by many folds over the years. This demand is due to various reasons like low-cost airlines, affordability to middle-class people. These are some of the reasons for increase in demand. If you see in this slide, there are a lot of people standing in the check-in lines. There are a lot of aircrafts parked in on the tarmacs. There are a lot of people waiting in the waiting halls, and there are a lot of aircrafts in there simultaneously. Though they may not be as close as it is shown over here, but there are a lot of aircrafts which are in air. So what uh, it indicates is there's a lot of demand for civil aviation and for civil transport and cargo operations. In the same way, we have a lot of demand for military operational security. Some of the reasons for increasing in military operational security is because of escalation of political tensions between countries and transgressions between neighboring countries. This has led to increase in operational capability, military operational capability of every country. Therefore, most of the countries have high number of aircrafts, high number of aircraft carriers, choppers, and all that. So what it tells is that there's a lot of demand for both civil aviation and military aviation. When we have this kind of demand for the aircraft, definitely there would be a corresponding demand in the maintenance. Now we will see what is maintenance, who does it, where it is done, and why it is done. Any activity that is carried out on a machine in order to bring the machine back to its original condition or to a state of functioning level is called as maintenance. Who does it? It is done by a maintainer. The maintainer could be an engineer or a technician. Where it is done at various places like tarmac, shop floors. It is done at engine bays. It is done at module change workshops and test beds. So various maintenance activities are carried out at various places for various preventive measures. Why it is done? It is done to increase the life and prevent premature failure of the engines. Aero engine maintenance includes overall repair, inspection, testing, modification. Gas turbine maintenance checks are periodic inspections that have to be done on all military aircraft after a certain amount of time or usage. High-end dependable serviceability is critical for efficient operation of aircrafts, both in commercial and military aviation. This is very critical. We need to have aircrafts available for civil aviation. If you do not have an aircraft that is readily available, then there is a loss of business, and there would be some maintenance and operation costs associated with it. So from the military perspective, the aircrafts uh, will be operationally ready for various combat operations and combat training. So high-end dependable serviceability is very, very critical. Most of the gas turbine maintenance establishments nowadays are facing problems like long delays, low serviceabilities, high downtimes, high lead times. These are some of the problems which have to be addressed seriously. And effective supply chain management and maintenance can ensure high serviceability levels of aircraft. Now we'll move to the generations of aviation maintenance. In the first few generations, uh, the aircrafts had to be had to take the ground equipment, and it had to be airlifted along the aircrafts when they move from one base to other base. When they ferry out from one base to other base, they do not have any ground equipment available when they land in some other base. That was a big handicap in the first few generations. And the first three generations, there was only reactive maintenance. We used to fix the problem only when the problem comes. There was no preventive maintenance or condition maintenance uh, uh, carried out. The fourth or the current generation does not have such problems and includes periodic major overhaul of engines, unit assemblies, and auxiliary equipment. Now, getting into the types of aero engine maintenance, we have basically two types of maintenance. Uh, One is corrective maintenance, the other one is preventive maintenance. Corrective maintenance is a reactive kind of maintenance. It is basically a passive kind of maintenance, something which is done after the problem comes. So if any repair or rectification is carried out, uh, after the problem comes, then it is considered as a reactive maintenance or a corrective maintenance. We'll be correcting it and bringing it back to its original condition. And we have a preventive maintenance wherein we take some preventive measures. We carry in scheduled maintenance and all that. We'll be having some condition biased maintenance also. It is purely based on the number of hours, and it is something which is done before the problem comes in. So it is basically a proactive action that is done in the maintenance establishments. So maintenance is divided into corrective maintenance and preventive maintenance. And again, corrective maintenance is divided into immediate maintenance and deferred maintenance. Immediate maintenance is something which has to be addressed. I mean, in order to make an aircraft or engine readily available for the flight line, or for the operations or to put into service. It has to be put into service back immediately. So corrective maintenance can be of two types, like immediate and deferred. Deferred is something which can be delayed slightly and which doesn't require more immediate attention. Coming to preventive maintenance, we have predetermined maintenance, which again classified as scheduled maintenance. Scheduled maintenance is like um, carrying out at scheduled intervals like 124 hours, 250 hours, 500 hours, 1000 hours, 2000 hours. I mean, this preventive maintenance is um, directed by the original equipment manufacturer engine is uh, uh, when the engine is sold out to the consumers or operators. So the preventive maintenance schedule is mentioned in the aircraft maintenance manuals, in the engine maintenance manual, and the propulsion manuals. Coming to condition-based maintenance, this is something which is carried out based on the condition of the engine, and something which is not done or purely based on the number of aircraft hours. So it is done based on the condition. We'll have some equipment to monitor its condition, like we'll be having some sensors, we will be having some neural networks, computational intelligence, and all that. When the condition becomes serious, then only the maintenance is undertaken. Uh, Now we will get into the levels of maintenance. There are different levels of maintenance, like we have line maintenance, shop floor maintenance, um, bay maintenance, we have test bed maintenance. Normally, the line maintenance is first line servicing. It is otherwise called as first line servicing. The bay maintenance is called as second line servicing, and the module change workshop, and then BRD maintenance is called as third line oblique fourth line servicing. So in civil aviation, uh, uh, these maintenance levels are addressed with the different names like A, B, C, and D check. Like as the maintenance level increases, I mean the level of maintenance that is carried out will be increasing. If you see over here in this image over here, there are some fighter aircrafts parked on the tarmac, and these aircrafts are uh, are in serviceable state or in serviceable condition, and they are ready to fly. So if any minor problem comes in, and if that minor problem is addressed or rectified on the tarmac in the line maintenance, then it is called as line maintenance. So here we will not be taking up uh, maintenance issues related to higher level. We will not be carrying out any major modification, etc. So, and here during nights, uh, the maintenance personnel are not permitted to carry out any maintenance activity, whether it could be minor rectification or anything. So, any minor rectification which is to be carried out, it has to be done only during the daytime. Uh, And in the first line as well as in the second line maintenance, there are maintenance personnel who are trained in some specialized trades like airframe structure, So these people will be dealing uh, only problems related to the structure or airframe of the aircraft. And the propulsion people will be dealing any problem which is related to propulsion systems. So here are some daily inspections, oil charging, uh, fuel refueling, tire inflations, and such things are carried out over here. Systems specialized trade is something which is associated with electrical and instrumentation, and avionics is something which is related to radar and radio trade. Then coming into the weapon and armament, this trade doesn't mostly exist with the civil aviation. This trade is available only with the military people, wherein the tradesmen or the engineers they fit some weapons in the weapon installations of the aircraft. They may be fitting some bombs, missiles, some launchers, laser guided bombs, and so on and so forth. As I said, we have a second line maintenance. Like uh, here in this image, if you see, the engine has been uh, stripped off here and it has been brought down. That means the engine has been removed for some major modification or major rectification. And here the engine is fitted, it is in installed condition over here. Here, major modifications, scheduled maintenance, preventive measures are carried out. Here, will not be taking up any minor maintenance activities. And in this picture, we can see some HL people working on some Jaguar aircraft, carrying out some modifications. This is also carried out on the shop floors. And coming to engine test bed, here you can see the engine is hung to a thrust stand over here, and we have a load cell at the rear side of this engine to measure the thrust. Whenever engine is operated or started, the thrust is measured with the help of a load cell which is fitted at the rear side of this engine. And you have a ramp over here. This ramp carries maintenance people near to the engine to carry out some fitments. They may be fitting some sensors which are again connected uh, to the engine control room, and those sensors are linked to the database of the control room, wherein they will be measuring the parameters of different components of the engine. So normally here the control room is not visible, but it will be on either left side or right side of this test bed. And this test bed, is acoustically made, and some noise suppressors are used. Anyone who is standing or sitting outside the test bed cannot hear the noise of the engine. So it is completely acoustically made. Here you can see in the previous image, the ramp had gone up to the engine. Now the ramp has come down. Uh, Now coming into aero engine maintenance establishment. Um, any typical aero engine maintenance establishment, whether it is uh, military maintenance establishment or civil maintenance establishment, it comprises of a maintenance control center and different levels of maintenance, as I said, like first line, second line, and third line. Now coming to maintainability, availability, and reliability. Uh, These three are very important metrics uh, to gauge the performance of the engines. Some of the maintenance establishments are using these metrics uh, to diagnose the problems, to understand the performance and the condition of the air engines. And these metrics uh, uh, have been given some formulas, and these formula have been uh, derived after carrying out extensive research, uh, research by our predecessors. If you can see over here, maintainability is the ability to maintain the aircraft. Availability is a very critical metric which has to be measured regularly. As uh, as the aircraft or engine is not available with the operator, then he would there would be cancellations of flights. There would be delay in flights. So there would be loss of my operation costs over here associated. And this is very critical metric which has to be included in the maintenance planning. And then the availability is also important for military also. If the aircraft or engine is not available for operation or for any emergency, it is a big bottleneck. It has to be operationally ready. So availability plays an important role in uh, eliminating uh, uh, bad reputation, loss of cost, etc. Reliability. Coming to reliability, reliability is a very important factor, which is something related to safety. Any engine comes with some kind of reliability. For example, the objective of a design engineer is to design the engine to its maximum life without compromising on safety and reliability. When he or she designs the engine, he designs it to its optimum life. For example, let us say an engine has a total technical life, um, uh, let us say 3,600 hours given by the design engineer. So, after considering many factors, after doing extensive research, so the total technical life has been given 3,600 hours. So, and uh, the major rectification will be done at 1200 hours, the first major rectification, and second major rectification will be done at 2000 hours, 400 hours. And by the time it reaches to the third rectification, it will complete its total life, and it has to be removed from the flight line. So the objective of the design engineer is to design the engine for its optimum life. Then what is the objective of the maintainer, whether it is the engineer or it is a technician? The objective of a maintainer is to take this life as close as to the design life. That is very important. For example, if we are able to take the life of this said engine to around 3,400, if we can pull it to 3,550 or so, touching the design life, that means the maintenance have done an exceedingly good job. So the reliability and availability are very critical metrics from maintenance and operations perspective. Now coming to gas turbine faults, when we look at gas turbine faults, Aero engine deterioration is majorly caused due to gas turbine faults. Uh, why? Because gas turbine engines operate on a wider range of operating conditions, a wider range of pressures, temperatures, and it operates in some hostile environmental conditions. So sometimes they may be operating, for example, from military perspective, because of the transgressions, recent transgressions between China and India. So some aircrafts have been moved to the forward base near Ladakh over there. It is at high altitude. You will not be having much air over there, and on top of that, you have a lot of sand and dust present in such kind of atmospheres there. So when you have such kind of atmosphere, when you are operating in very hostile operating and environmental conditions, the gas turbine engines are subject to the inherent deterioration and degradation. Um, so gas turbine faults are very critical in increasing the serviceability levels of the aircrafts. I mean to say these have to be addressed. Let us see this bathtub curve over here. On the y-axis, we have failure rate. On the x-axis, we have timing. When the engine comes out from the assembly line and it gets operated and uh, its life keeps on increasing. Initially, we will have high failure rate. This is due to burning because of the rubbing and all that takes place during the initial phase of the life of the engine. This is called as infant mortality in technical terms. This is the burning period wherein the failure rate is slightly on the higher side. And it slowly, as the time passes, as the life of the engine increases, the burning comes down, and the failure rate slowly drops down, and it gets stabilized at one point of time, and it remains almost all. It was that line, the operating line, and then towards its end of life, as I said, the total technical life. For example, as we were discussing about the 3600 TTL of an Aero engine, when it is approaching towards that, when it is nearing, the wear out again increases, the failure rates will become more uh, will be higher, and they become more important. These have to be, this is where the failure occurs, and this is where the maintenance comes into play. This is where the condition-based maintenance, the digital twins, and all new technologies will come into play, and to uh, decrease the failure rate and take it close to the TTL. That's very, very critical. Now we will see some of the gas turbine faults over here. The first one is the fouling. Fouling is something like a deposition of sand, dirt, and dust on the compressor blades. When we have some deposition on compressor blades, the flow capacities will come down. The compressor efficiency falls down because the aerodynamics get disturbed. The compressor is not able to suck in the amount of air that is required for the engine for the operation. So fouling has to be addressed. So what is the potential solution to address this fouling issue? The potential solution normally employed by the maintenance establishments is LP compressor wash, regular washing of the compressor blades, increases the thrust slightly, so which has come down because of falling. It has to be monitored continuously uh, at regular intervals. Someone has to go inside the air intakes and check in any deposition of sand, dust, dirt, or we can also have some carbon deposits over there. Even slight deposition of carbon deposits will have a tremendous impact on the performance of the engine, and it becomes very critical from military perspective when you are not able to have the required thrust that is set by the OEM. You can be shot in air if you have a slight fall of thrust. For example, if you're holding at 98.5 instead of 99, the enemy can hit you. So these gas turbine falls has to be addressed. The next gas turbine fault is corrosion. Uh, there are two types of corrosion. Like we have a wet corrosion and hot corrosion also. Wet corrosion is something which is associated with moisture and water. If you're operating in bases like Jamnagar or Chennai and such places where you have more moisture and all that, then the compressor blades are subjected to corrosion development. When you have corrosion over a period of time, it eats away the material, and there would be some loss of material in the compressor. When there is a loss of material, we may think that more air will come in, but in fact, it doesn't happen. The compressor doesn't suck in more air. The flow capacity falls down tremendously, and then it will have a tremendous effect on the efficiency of the compressor. But if you look at the hot corrosion, which we have been discussing, this is something which is related to turbine. So hot corrosion normally occurs in turbine, and this occurs due to unburnt fuel which is left downstream of the combustor. When you have ineffective combustion that is taking place in the combustor, you will have some unburnt fuel that is coming out, and which may lead to corrosion development. And this is very, very critical. So it eats away uh, some part of the material of the turbine. So there would be a loss of material over there. But here the flow capacity will increase, because I know it will pass through here. It is the reverse case of the compressor. The flow capacity will increase, but the efficiency falls down. Why the efficiency falls down? You are not able to use the hot gases to convert into the work. The energy is not able to be converted into work just because of this hot corrosion. So how this corrosion can be addressed? This can be addressed by taking some preventive measures like um, uh, corrosion preventive actions and control programs. Like we can apply some chemical solutions for the blades, both. Mostly we can do it for compressor. It is slightly difficult to carry out to the turbine, as it is remotely located downstream of the combustor. Um, then we will move to the erosion. Erosion is a very serious problem, and normally it occurs in if you have airstrips and runways full of dirt and dust, and if the runways are not cleaned regularly, um, then the engine may pick up some hard particles. It could be some small stones, or it could be some metallical particles also that can be sucked in. They may go and hit uh, the blades. So there would be a similar damage like corrosion. In corrosion, it was oxidation of material. Here, it's direct physical damage that is done. Sometimes you may lose some material. Uh, so we can name it as foreign object damage over here. So when a foreign object damage, FOD goes in and hits, there would be a loss of material, and in turn the material which has come out may hit another component. Then it becomes a secondary damage. There are a hell lot of problems over here. This again, we need to maintain some clean airstrips, clean runways, clean taxi tracks whenever the aircraft rolls out for taking off. We have to ensure that it is maintained, and we should not leave it as unmaintained. So next, coming to an important gas turbine fault, that is rubbing wear. Rubbing wire is an important gas turbine fault which normally occurs because of thermal expansions. Um, as we all know, gas turbine engine is subjected to very high temperatures, and it will have um, uh, mm, a thermal expansion due to high temperatures. And when there is a thermal expansion, there would be an elongation of the material, and the blades would be going and touching the casing. When they go and touch the casing, uh, um, so again, loss of material, and then the entire operation of the engine will be disturbed. Rubbing wear can also occur because of misalignments. During maintenance activities, if we deviate from the maintenance procedures that is set by OEM, then I mean, if there is any misalignment, eccentricity, and during heavy landing also, it may lead to rubbing wear, wherein the blades may close in the gap and may sometimes touch the casing of the engine. Then moving on to labyrinth seal. Labyrinth seal is also a gas turbine fault. It normally prevents any leakage of oil or that sort or air from suction to the discharge side. Uh, it will not have much effect on the flow capacities, but it will have slightly some impact on the efficiencies. Foreign object damage, I have already discussed. Any object that comes in, I mean, during maintenance also, if, for example, there was an incident while I was working on Hawk, wherein the maintenance personnel could not check in the loose spot of an air intake guard. It was left like that. The loose spot of that air intake guard, which prevents normally FOD, has taken in. It was taken in and it had gone and it had hit. It had done both FOD and DOD, domestic object damage. And coming to the hot end component damage, um, here the hot end component damage normally occurs in the turbine blades downstream of the combustor. When there is an ineffective cooling, normally the trailing blades, the trailing edge of the turbine blades will have uh, less access for the cooling air. Uh, so when you have less cooling air available at the trailing edge of the aerofoil, then it may lead to some hot end component damage. Now, here you can see what kind of impact these aero engine faults have on component performance, and how they result in or lead to a change in parameters. For example, if you see, these gas turbine faults will have a tremendous impact on the component performance. And when there is some abnormality in the functioning of the component, definitely there would be some changes in the parameters that can be monitored by the pilot, by the technician, or by the person who is giving the ground run. Could be an engineer or a technician, or it could be a pilot. It can happen in air also. You can see there would be some changes in the component performance, like the compressor efficiency, the high pressure shaft speed may fall down. So it could be because of any of the reasons, and uh, and it will have a tremendous impact, and it will result in changes in parameter. This, if we are able to measure these parameters properly using condition-based maintenance or any other uh, uh, emerging technology like digital twin and all that, then we can reduce the maintenance problems, and we can make the engine or aircraft available. So we will have less downtimes, less lead times. And if you see over here, so as I said, this is falling. There's a lot of carbon deposition. Uh, uh, if you see here, it's falling here. There's a lot of carbon deposition here, erosion, and as well as deposition, bird heat, tremendous impact on the starboard side of the engine. So we can see the bend to the lip of the air intake is disturbed. And if you see here, because of bird heat, there's damage, and here there's a lot of ash, and here FOD a damage. And coming to the fatigue, bird loss due to, sorry, blade loss due to fatigue. So I mean, fatigue can occur because of high cycle fatigue, low cycle fatigue, thermal fatigue also will be there. High cycle fatigue normally occurs because of aerodynamic exertion, self-exertions, and some stresses and all that. And low cycle fatigue is something uh, uh, which occurs because of frequent starting and stopping of the engines. Especially low cycle fatigue occurs in the older engines. And thermal fatigue, we all know. We all understand the creep. It is the plastic deformation of a material when the material is subjected to high temperatures and high stresses over a period of time. So we may have creep on such kind of problems over there. So, and this fatigue has to be monitored, and it can be monitored using vibration monitoring systems like using transducers, accelerometers, which are connected to the engine. Coming to the systems monitoring, some faults, we are not able to identify or recognize most of the faults of the engine. Some faults go unnoticed, and in order to address those faults which go unnoticed, we use systems monitoring. See, here we have oil system monitoring, debris monitoring, vibration monitoring, engine usage monitoring techniques, visual condition monitoring techniques, turbine exit spread monitoring, limited transient monitoring, acoustic monitoring. Um, I will I'll discuss slightly briefly about these. Oil system monitoring can be done by regularly checking the oil systems, oil tank. Um, I mean, if there is a over consumption of oil, if you observe any abnormality in the consumption of oil, then we have to confirm there is some problem. It could be because of leakage of oil, and there could be damage to the bearing. And because when the bearing damages, when engines are normally subjected to high vibrational stresses, centrifugal stresses, heavy loads, and so bearings may sometime get damaged, and bearing seals also may get damaged. When bearing seals get damaged, the oil will leak in. So this is very critical thing. When the oil leaks in, in order to prevent the oil to get into the other subsystems, we use some air which is tapped from the cold section of the engine, and which will be put in the opposite direction of the oil to prevent its leakage. But it cannot withstand for more time if there is a continuous leakage, and this can be identified from components like centrifugal breather, wherein you will have more air there because the air is trying to stop the leakage of the air, and so it has to separate the air and oil over there. There we can identify if there is any damage to the oil system. Debris monitoring. So if there is any damage to the bearing, the metallic particles will come from the return lines of the engine, and it can be collected at the MCD magnetic chip detectors, which are fitted in the return line. So magnetic chip detectors, they collect any metallic particles that are deposited which come through return lines. And if you notice more debris, then we have to conclude that there is some abnormality. And vibration monitoring techniques, as I said, the engine is subjected to high centrifugal vibrational stresses, especially when during military operations, when the engine is climbing up, doing dogfight, chasing, and all that. So during takeoffs and all, there would be heavy load on the. If there is any fatigue and if it leads to some vibrations that can be captured using sensors. So we have accelerometers and transducer to capture the vibration. And coming to the engine usage monitoring systems, there are various types of monitoring systems like visual control systems are there, wherein we use fibroscopes and endoscopes to see any damage development in the remote places of the engine, like if there is any damage or there is uh, uh, any FOD, if there is any coking, so ineffective combustion, deposition of carbon and all that, that can be identified with the help of fibroscope. It's a very flexible, it has a flexible lead with a light source which can be moved all over the place inside the combustor or turbine. We can even see any deviations on the turbine blades, any crack development, any nicks, dents, and all that. That can be done with the help of fibroscopes, endoscopes. Boroscope is a rigid one. Fibroscope is something which is flexible, and it is also called as endoscope and all that. So turbine exit spread monitoring, we have thermocouples fitted at the downstream of the turbine circumferentially to monitor uh, uh, the heat that is developed. If there is any abnormal uh, heat development at one position, for example, there's more heat development at 7 o'clock position of the thermocouple, then we have to investigate the problem. So it could be because of ineffective cooling, there could be some problem. There could be some problem in the bleeding of the air and all that that goes into cool the hot section. And then the limited transient monitoring, we do a lot of monitoring, like we see the rundown times of LPC, rundown times of the HPC. So it comes under limited transient monitoring. So rundown times means it is the stoppage of the compressor, like LPC. Uh, LPC may take more time because it is fitted to a free turbine. It doesn't have any load, but a HPT takes less time. So as um, uh, as it is connected to the accessory gearbox, which in turn drives a lot of accessories. Um, that can also be identified when there is any abnormality in the rundown times. So, um, the acoustic monitoring, again, this is something which is related to, again, vibrations. If there is any abnormality, we can find out that abnormality in the engine control rooms when the engine is tested at test bed level. Now, if you see this image over here, the breakdown of faults detected for Aero engine. Uh, um, the the major problem over here is oil. As I said, this is very critical because the bearings may get damaged, and then So oil lubricated component problems are more in numbers, and 24%, and oil leakage is 28%. That's why I have emphasized on this. So these are the major problems that are normally occurred in the flight operations, whether it is civil aircraft or it is military. And in this slide, we can see that we are using all these monitoring techniques, and we are integrating and trying to uh, predict failure and remaining useful life of the engine. Yeah. We have vibration monitoring, all system monitoring, visual vibration monitoring, all system monitoring, visual inspection, uh, exhaust temperature mounting, and all that. So using this, we can reach to a conclusion about the state of the engine or condition of the engine. Moving on to the current developments, which is our main topic here. Um, Condition monitoring is something which is carried out based on the condition of the engine. It is something which is not done purely based on the number of hours like we do in preventive maintenance and scheduled maintenance. This is purely done using some sensors, using some computational intelligence and all that. Uh, the important thing over here, when we carry out condition-based maintenance, we will not be pulling out the engine from the flight, from service, or from operation. Uh, just because we'll wait until the condition uh, becomes worse. Until then, we use the engine. We will keep it in operation. So, whereas in preventive maintenance, the engines have to be brought down and have to undergo uh, preventive maintenance. Like they have to come at 125 hours, 250 hours, for example, few 500,000, 2,000. That many times the engines have to be brought down. So when you bring the engine that many times, several times down, you are losing a lot of operational costs. You are losing big business. So I mean, there would be a lot of delays, cancellations, and all that. So for unnecessary maintenance. Uh, Condition monitoring aims to continuously observe wear-related variables throughout a system's lifetime to determine its degree of deterioration. Here you can see the action taken after each inspection depends on the state. It doesn't depend on the number of hours. So this condition-based maintenance is done. It has a procedure. It is done in some steps. Like we have a data collection, data analysis, decision making, uh, implementation. In the data collection, so what we do is we collect the data. We have the process data, failure data, whatever data that is collected. So the data will be captured, it will be analyzed, and then a decision is made whether a maintenance has to be carried out or not. If you see, there are four uh, methods which are normally used in the condition-based maintenance. One is the analytical-based. The other one is model-based, knowledge-based, and hybrid-based. Analytical-based is something which focuses more on the process data, like focuses more on the parameters, any changes in the parameters, any abnormality in the parameters, any deviations in the parameters. And then it also uses some failure data, which can be obtained from the systems monitoring. This is physics of failure technique. Here in the model based, we use statistic techniques. What is statistics technique? Here, we use historical data. We use past failures, present failures, and based on that, we will predict some future failures. And in the knowledge base, it is
It is uh, it is done purely based on the experience of the technician and the engineer. Um, Here, the experience, the exposure to different types of aircraft, different types of engines, so to different emergencies comes into play. So the experience plays an important role in making the judgment whether we need to go for maintenance or not. In the hybrid based, it is a fusion technique wherein we use all the combined methods. We combine all these methods and we come to a conclusion. We arrive at a conclusion. This is the taxonomy of remaining useful prediction methodologies and techniques. Here in this graph, if you see remaining useful life graph, on the y-axis we have system health index, and in the x-axis we have times. If you see this line over here, it is over a period of time it is falling down. Initially, it was in the healthy regime, and then it moves to the caution regime as the time progresses, as the time elapses. Then it gets into the repair regime, wherein it requires some repair to increase the life. And then it reaches to the failure regime here. So this is the remaining useful life, and here we need to carry out a lot of maintenance activities. And when it reaches to this point over here, then it has reached to the failure uh, state. Now coming to the digital twin, if you see, there are two aircrafts over here, one on the left side, the other one on the right side. Right side one is the digital one, that's a digital twin. The left side one is the physical twin. It is a virtual representation of an Aero engine that uses computational models to predict failure and mine useful life. Now, this digital twin captures all the data right from its first flight. It captures accurate data from the physical twin. So some sensors will be fitted both on the engines as well as on the aircraft, and then um, the data is transmitted to the digital twin, uh, which we will have in the control rooms. So that data will be transmitted to the databases, to the computers, wherein we'll be monitoring the condition of the engine. It it almost all captures accurate data, and it helps in mitigating the damage. Uh, and it almost all, it mimics whatever this one does, it does the same thing. So we'll be having first-hand information sitting in a control room, how the aircraft is operating in air, how the engine is operating in air. If there is any abnormality and if there is any maintenance that is required to be done when it lands, we will have that freedom, and we'll have that opportunity to procure spare parts, to make the spare parts available for its maintenance, and make it ready for the next flight. So this is the game changer over here. So uh, as I said, it continuously tracks the physical twin and how it is being used during its entire life cycles since it comes out of the assembly lines. And it eliminates unnecessary maintenance. When we have first-hand information of the condition of the engine, we don't need to go for preventive maintenance. We don't need to take the engine off from the aircraft and go for maintenance. We'll be saving a lot of money, uh, and we'll see in the next slide. So um, the current maintenance model is purely based on the number of hours, and So it is carried out at scheduled intervals, and we need to, as I said, we need to take it out several times during its course of life. Uh, uh, what are the demerits of it? Is highly expensive to take out the engine that many times. The parts have to be replaced. New parts have to be bought and then fitted. So there's a lot of money that is going on here, and it puts your engines down from service and operations, resulting in loss of business. And it increases downtime, so the availability comes falls down. Um, uh, And if you get into the benefits of digital twin and digitalization, it allows to carry out maintenance of your engine only when it is necessary. So, so when it is not necessary, we will not be going for any maintenance. Uh, it reduces the maintenance time to fix the problems because we will be having enough buffer available on the shop floors to fix the problem, because we have come to know about the future failure in advance, well in advance, before it comes down, before it touches down. So, and the earlier systems used to have like Microsoft Excel and all that to store the data. But this digital twin uses machine learning and artificial intelligence to store and compute data. Here we can store enormous amount of data, and it forecasts key performance indicators. uh, like number of engines, number of modules, like performance indicators like NH, TGT, and such things, thrust and all that. And it captures failure modes associated with different aero engine components. It could be a compressor, uh, it could be a diffuser, it could be a combustor, downstream, it could be a HPNG, HPT, LPNG, LPT, it could be exhaust, afterburner, such things. So, um, but this application is not just limited to aerospace. This can be used to power plants. This can be used where power is generated. The power plants can be used both for power generation as well as to power the aircraft. So, and we are even powering automotives with the help of power gas turbine plants nowadays. We all know. So the advancements that are going on in the automotive side also. So it can be applied to wind turbines, offshore platforms where we produce oil and gas. So this has, multiple advantages. Coming to this slide, if you can see, this is not just limited to only aviation operations or airline operators. This can be used for maintenance operations also. How the maintenance people are carrying out maintenance, how when the component is fitted, when the component is removed, when the engine has arrived to the shop floor, when the engine has left from the shop floor, what is the lead time. Such things can also be done with the help of this digital twin. It can be applied to supply chain logistics also. This is all extended learning enterprise, and as we all know, this is used for engine characteristics. Here I'm showing some um, uh, windows of the software which is being used by Siemens for some clients. So you can see the engine serial number. This has been taken from Siemens. You can see here a lot of engine serial, different engines with the different serial numbers, operating hours, and all that. There are some key performance indicators, number of engines, modules, and other things. Um, Hours, everything is given here. engine spare pool size. So the graph is number of those which are out of operation, how many shop visits per year, how many times it has come. Um, Now coming to lean maintenance, yeah, if you see in this slide, um, there are things like non-value added time, value added time, cycle times, and although the process time is 2 days over here, the value added time is 1 day. We have wasted 1 day for various reasons. So if the lead time is 3 days or 4 days, and the value added time is only 1 day, then there is a loss of 3 days. So if you can see in this slide, normally, as I said, any maintenance establishment will have some control center which monitors the life of the engine or aircraft, and which informs the operator that the engine or aircraft is due for service. This control center over here informs the operator, and the operator hands over this engine to the propulsion bay over here to carry out minor stop preventive maintenance, which is normally done at 2,000 hours or so for a Hawk engine. So when it gets handed over to propulsion bay, then it undergoes various processes. Um, Various servicing activities are carried out. We'll have some processes before it is made available, and it is brought to its original state. So uh, from here we can come to know the total lead time is 24 days, but the total value added time is only 14 days. That means we have wasted 10 days over here. There's a lot of 10 days. That means the engine was not available for operation or for service for 10 days. This is a serious issue which has to be, we could have finished it uh, in the shortest time of 14 days itself, or 15 or 16, if we have addressed the problem of non-value added time. Uh, what are the main reasons for increasing non-value added times? Like waiting is non-value added work. Because of the non-value added work, the non-value added time is more. So the waiting time for spare parts, tools, testers, ground equipment. Sometimes you have 6 aircrafts on the shop floor, and you may have, for example, you need to have a CSD, you need to have a PSD, you need to have vibration monitoring test set. Such things, if they are not available in right number, you need to have speed drive and such things. If you do not have in right number, so you'll be able to do service only for 3 aircraft, because only 3 tools are available. And if you do not have right ground equipment for carrying out, if you do not have the hydraulic systems, uh, anything it could be, so it will add up to a lot of non-value added time. Unnecessary transport is something. If you have a poor utilization of the space on the shop floors, so you will have unnecessary transportation if the tool crate is not located at the right place and the engine bay is not located at the right place. Um, so it will take more time to to walk into, so, and even to get some parts from the logistics, it takes a lot of time. We should have very less inventory that should be available. We need to have only right amount of inventory. Any excess inventory will stop the flow. Will not have a continuous flow. If more inventory is available on the shop floors, so technicians won't be able to move freely. So that is one thing, and there would be additional costs. Unnecessary inventory will be there, unnecessary movements. And the other thing which lean addresses is it empowers employees, uh, employee creativity. It encourages if it doesn't wait for higher authorities to standardize something. It encourages the budding technicians, budding engineers uh, to have a freedom in the decision making. Uh, if some new thing has been uh, uh, invented or if new thing has been found, it will be standardized and it will be approved by the entire organization. So standardization is very, very important. The lean metrics like cost, quality, safety, and all that. So elimination of waste, this Mora is something which talks about that. And we have Mora and Mori, which focuses on unevenness and then overburdening. So we should not put a lot of load because we may have very less people available. The training, the skilling is also very important. We have to ensure that the maintenance personnel are trained or upgraded. So their skilling has to be continuously monitored. And there should be some continuity with programs. And we need to maintain some a record of the skill. For example, a maintenance establishment should know how many engineers can give ground on, how many technicians can give ground on, how many engineers can fit the gas turbine starter or air starter. I know how many technicians and engineers can do module change work and such things. And accordingly, we need to upgrade our skills. So lean for emphasizes on skilling. This is very, very important. And we learn only when we are allowed to do it, and from our mistakes only we learn. Now we should be given any more freedom. And we all know the Japanese work ethic. They all focus uh, on reducing the waiting time, reducing the inventory, reducing the defects, reducing the uh, repetitions, and that is also very important. There should not be uh, any repetitions in the work. It takes more time if it is not done properly. Now coming into the role of logistics and supply chain, the main aim of logistics is to track and procure the parts that are not available with them. Uh, some of the uh, key points over here is demand forecasting. This is an important job of the logistics. They should be in a position to demand forecast. Uh, they should be in a position to forecast the demand. So provisioning is something which is uh, means forecasting demand based on past utilizations, present utilization, and future utilization, and accordingly procuring the parts. So provisioning plays an important role. And then close monitoring of space. It is the job of the both maintainer as well as the logistics. Some there are different kinds of parts. We'll see over here. Like we have life limited parts and we have on condition parts and we have some consumables over here. Life limited parts are those parts which have life and they have to be replaced when they complete their life. And on condition parts do not have any life and um, they are replaced based on condition. But the life limited parts become critical spares when they approach towards their life, they have to be replaced. We have to ensure that we have enough number of buffer. And consumables are parts which are normally replaced uh, during every maintenance. Mostly these are replaced. These are seals, rubber seals, gaskets, and all. Portables are the parts uh, which can be repaired and put into service. And here, if you see, there's an interrelation between health and usage monitoring systems and supply chain management. Uh, what we have to understand is we have to give more importance to health and usage monitoring system, condition-based maintenance, and digital twins and all that emerging technologies. Based on that, we have to define buffer. Once we define buffer, we'll be in a position to get those parts readily available. So when we have buffer, we will not have aircraft on ground or POG on ground due to lack of parts or spares. Uh, some of the drawbacks of the current procurement system are like they have access to only local and regional suppliers. They do not have access to global suppliers. And there is scope for counterfeiting and all that. So counterfeiting is something like using an unapproved part, substandard part, which looks similar to the original one. So there is a scope for counterfeiting as this system is not encrypted and it is not fraud proof also. And the current procurement systems are slightly slow on the slower side. And if you introduce blockchain, we can increase traceability. It is fully encrypted. We can be connected to the global suppliers. We know some part like fuel control unit, which may be available in remote places like Africa also. Transparency and visibility as the transactions are made visible to everyone. This becomes more transparent and the visibility increases. Everyone knows about it. And uh, as I said, it is fully encrypted, fraud proof, and uncorrupted. And supply chain includes suppliers, manufacturers, distributors, end customers, operators. And supply chain integration helps in achieving continuous flow on shop floor, low inventory, and effective demand management. Some of the challenges that we have here is low serviceability, availability, safety and reliability, reduction of downtime and lead time. The above four can be addressed by having condition-based maintenance and uh, by having new technologies like digital twins. Skill training, I said that this is very, very important. The skill gap has to be reduced. Elimination of counterfeiting, this can be addressed by using uh, technologies like blockchain and all that. A reduction of maintenance and operating costs can be brought down if we can use condition-based maintenance and digital twins. And some of the challenges are adoption of new technologies. There would be some kind of resistance in the employees to adopt new technologies when they are introduced into service. So we have to make them aware and we have to make them understand about the benefits of new technologies. And when we have all this, the responsiveness will definitely increase. Some of the opportunities that exist for budding aerospace research, both in um, uh, 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 local and global side, they can have opportunities in our nations like DRDO, GTRE, NAL, DRDL, DARE, DRD, Defense Services, HAL, ISRO, Air India, and they can also have some opportunities globally in NASA. In public sector, there are some people being recruited even in Ministry of Defense UK when they clear a security clearance. So you can work in global airlines, Etihad Airlines, Lufthansa, and so on. Uh, so you have plenty of opportunities for budding aerospace engineers, maintenance engineers, scientists. So we also have some opportunities in private sector locally, like Tata Advanced Systems, Mahindra, Tanuja, etc. And we have global opportunities like GE, Rolls-Royce, Honeywell, Pratt& and Whitney, Snap-on, Turbomeca, GKN, Global Quest, and so Boeing, Airbus, British Aerospace, Dassault Systems, Lockheed Martin. And we can get into the academy also as researchers, scientists, some of the roles that are available are like they can become aerodynamics, thermodynamics, component design engineers, aircraft aero engine maintenance engineers, aerospace vehicle and propulsion design engineers, airline operators, space engineers, safety engineers, etc. So there are a lot of opportunities that exist both locally and globally, both in private and public sectors. You can see some of the logos of the companies like Boeing, Raytheon, Honeywell, Lockheed Martin, uh, Pratt& and Whitney, GE, Safran, Turbomeca. And conclusion is the key to success in the future for aero engine maintenance is in the ability to identify uh, new technologies like digital twins, condition-based maintenance, blockchain, lean maintenance, and all that, and integrate and apply these new technologies to optimize maintenance with respect to availability, reduction of operating and maintenance costs, safety and reliability of aero engines.
Yeah, now those who are having any queries, you can unmute and you can ask. Now I request Ashwini ma'am to give the vote of thanks.
Okay, sir. So I extend my warm thanks to our director, Dr. K.S. Narayan sir, to giving us an opportunity to organize this webinar. I extend this opportunity to thank our speaker for today's webinar, Mr. Vidyasagar Kota, aerospace researcher and engineer, retired defense personnel IAF, for sharing his knowledge to all our students and participants. I also thank Niranjan sir and Sharat sir for organizing this webinar. Thank you, sir. I extend my thanks to all the faculty, students, and participants who have attended the webinar. Thank you, everyone. A feedback link will be shared to you. Kindly fill in the feedback link and send it. Thank you, everyone.
Thank you, ma'am. Yeah, now the those who are having any doubts, you can ask and you can get your clarification. Okay, I thank all the participants for joining for the webinar. So, if there is no queries, we are going to wind off the session. Thank you. Thank you all.